All right, so the whole point of this particular video is just to discuss wave vocabulary. And if you take a look at the website where you're watching this video, if you're watching it on my website, go and scroll all the way down to the bottom of the page. There's going to be a little Word document there that I've uploaded that you can print off and take notes on if you want. You don't have to. You can take notes on your own. No guarantees that I'm going to go in order on what that Word document is, but I will cover everything that's on it. So let's talk about the first two that are on the document, or just these two in general: mechanical wave versus an electromagnetic wave. Okay, these are two different types of waves. I know we talked about in class about longitudinal and transverse, and that's not necessarily the distinction here. All electromagnetic waves are transverse. Okay, but mechanical waves can be transverse. For any over here, transverse or longitudinal. One of the other things that really sets them apart is that an electromagnetic wave, which is basically light, that's what we're talking about here. Light is an electromagnetic wave, and it's light in all forms, and that's gamma rays, X-rays, radio waves, microwaves, regular visible light. That's all electromagnetic. And basically, what it is an electric field and a magnetic field that oscillate back and forth from each other. But that's not entirely important right now. But what you need to know is that all electromagnetic waves are transverse, and they require no medium. Now, what is a medium? A medium is simply material. It doesn't require material to propagate through. One of the plainest examples is that we get light from the sun, and the light has to travel through empty space in order to get here. So it does not require a medium like water or air or something like that, like some of the other waves do. Now, mechanical waves are things that require a medium. They have to have something to travel through. Sound is a mechanical wave, and it has to have something to travel through. We hear sound through air or any other type of gas. You can propagate sound through water, and you can propagate sound through a number of different things. But it requires that medium, the molecules sitting next to each other, in order to transfer that energy. So basically, an electromagnetic wave, which is light, is always transverse and does not require a medium to go through. Now, it can go through a medium, but it does not require a medium to transmit. A mechanical, on the other hand, is transverse or longitudinal, can be either one, but it does require a medium. It does have to have something to travel through. Okay, so let's talk about the difference between longitudinal and transverse. Okay, mainly the difference between longitudinal and transverse happens to do with the motion of the particles that make up the wave. Okay, longitudinal waves, like we did in class with the slinky, is motion that it goes parallel. So it's parallel motion of the particles. Now, what is it parallel to? It's parallel to the motion of the wave. So parallel motion of the particles to the wave direction. And you can rephrase that however you want to, but it basically means that the particles, if the wave is traveling this direction, then your particles are going to sit there and oscillate back and forth, back and forth, back and forth, parallel to the direction of the wave. Transverse, on the other hand, is perpendicular. And again, we're talking about the motion of the particles. So if the wave is going this direction, then you could have a wave hump like this where the particle goes up and comes back down. And that particle, that little thing right here, is just moving up and down, up and down, up and down as the wave goes through it. But the wave is traveling to the right. So it's perpendicular motion to the of the particles to the wave direction. Okay, that is the difference between longitudinal and transverse. Now, either one of these can be mechanical. Think about the slinky that we had in class. That would be considered a mechanical wave because without the slinky, you wouldn't have any of those kind of waves. And we were able to exhibit both longitudinal and transverse. Okay. So let's talk about a transverse wave. Okay, that is usually how we draw a transverse wave, and you can kind of see why we do because of the fact that it's really what it looks like. Okay, so let's talk about some things. So we have a crest. A crest is the absolute maximum amplitude of the wave. So this is the crest, the highest point in the wave. Okay, the trough is the one that goes down here. All right, that is the crest and the trough. So the trough would be considered to be the lowest point in the wave. Um, this could also be considered to be an amplitude. Both the crest and the trough are considered amplitudes. And that just means maximum displacement. So if you're at an amplitude, you're at a maximum displacement, either up or down, and that is the amplitude. Wavelength. A wavelength is the difference between two identical parts of a wave. So here between green and green, this right here would be considered a wavelength. Now you might ask yourself, well, this right here is a 0 point, so if you're going from 0 to 0, why didn't you stop here? This is not an identical portion of the wave, right? Up here, the wave is going up as we go to the right. Here, it's going down as we go to the right. So the next point where we're at a 0, where the wave continues up, is right here. That is a wavelength. And again, it's the distance between two identical parts of a wave. You could have a wavelength between this crest and this crest. That too would also be considered a wavelength. Again, the wavelength is in green. So the difference between two identical parts of a wave, that is a wavelength. Okay, so let's talk about frequency. So if we pick out a point on the wave, and I'm going to do this in, since we have the wave in blue, I'm going to do this in black. So we pick out a point in the wave. Now, as the wave is traveling this direction, that particle is just going to be going up and down, up and down, up and down between crest and trough, crest and trough. So the frequency is going to be how many cycles or how many of the waves, how many full wave lengths can pass through that particular point every second. So it's got a unit of cycles per second. It's also known as hertz, which is abbreviated as Hz. So the frequency is how many waves, how many full wavelengths every second pass through a given point. That is frequency. Period, on the other hand, is the exact opposite of frequency. It is how many seconds does it take per cycle. So let's talk about one particular wavelength. How long, how many seconds does it take to go one wavelength in direction? So how many seconds per wavelength, or how many wavelengths per second? This one is just measured, it's usually just in seconds instead of seconds per cycle. So a period is measured in seconds, frequency is measured in hertz, and you can almost see here that period is 1 over the frequency, frequency is 1 over the period. Big T is period. Frequency is lowercase f. Okay, how does this look like on a longitudinal wave? Okay, it's hard for us to draw longitudinal waves. So we pretty much draw it like a slinky. Okay, and this slinky has areas where you have really high compression and areas where you have really low compression. So the places that are really high in density, so say like this right here, this is known as a compression for good reason, right? You can see how it is just all compressed together. Okay, while the areas in between compressions where you have low density or the slinky coils are spread apart is known as a rarefaction. Okay, this is analogous to your crest and your trough on a transverse wave, but this is a longitudinal wave, and we don't have the same words for it because they don't look the same. So compression is going to be the places where you have most of your coils. Rarefaction is going to be where you have the least amount of your coils. Or if you're talking about density, highest density, lowest density. Okay. You can have a wavelength. I'll do it in green again. So the wavelength here would be from compression to compression, or you could have it from rarefaction to refraction. That is the same thing. Okay, we have a few more things to talk about, and I might have to push over this into a second video because YouTube doesn't like more than 15 minutes. Let's talk about refraction. Now, you don't want to get refraction and rarefaction uh, mixed up. They are two different things. Refraction is the bending of a wave as you go into a different medium. So the bending of a wave as it enters a different medium. And I'm sure you guys have all seen this. If you have like a glass of water or soda or something like that, and you have your straw in it, or if it's tea and you have a spoon, if you take a look at it on the side, you see the straw coming down, and then all of a sudden it's kind of a disjointed straw, and then it almost changes its angle. So that break right there, where the light of the straw changes direction at that boundary, that is refraction. Okay, that is refraction. There's other examples from it. You can see, people sitting in a swimming pool, how their bodies underwater don't look exactly the same. That's also refraction. So what is that, or how does that relate to diffraction? Diffraction is again the bending of light, or any kind of wave. So it's the bending of a wave as it goes around a corner or through a small opening. So bending of a wave around a corner or through a small opening. And the best way to exemplify this is, let's talk about sound. If you're walking through the halls here at school and you usually meet one of your friends at, say, like a crossroads between two hallways, and that friend happens to be really loud, you're more than likely able to hear the friend before you're able to see the friend. And that's just because sound typically likes to travel around corners. When it hits a corner, it'll bend around the corner. How do we visualize that? Well, if each one of these lines is a sound wave, as it goes to a corner, what's end up going to happen is that it just bends outward. And no matter where the person is, you might be able to hear it if you're sitting over here. That sound traveling to the right bends outward, and you're able to hear it. Okay, while we're talking about sound, let's talk about something known as timbre. Okay, if you're in any kind of music classes, timbre, you might know it. Timbre is simply just the quality. You can have many different instruments playing the same note, but they're all going to be sounding just a little bit different. And the reason for that is because they're all being propagated in slightly different ways, and that is known as the timbre. So it's the quality of the sound. How does it sound? Is it a voice? Is it a violin string? What is making the sound, or the wave? So the quality of the wave is known as the timbre. Okay, I'm going to stop here. I know there's a few more that are on the list, and I will post a secondary video because I'm starting to run out of time.